All right, so this is the last theorem that we had, when we took off last time. Let R be a commutative root of identity. Then this is a striking theorem because it's very different than what happens, polynomials. But there's a one-to-one correspondence between the maximal ideals of R and maximal ideals of pouch. And that's the way it works. So let him be a maximal ideal of R. Then MX is a maximal ideal of R. And we have noted this before because right? So given a maximal ideal here, its image here, and of course, I'll point out here that of course, this right here is maximal ideal. The curious part about this is that, and is it obvious to you all that if I have two maximal ideals, M1 and M2, then these are actually distinct here, right? Okay. The interesting part, of course, is that these are the only maximal ideals. And so we should see something that shows up that's different than what we could see in a polynomial case, and I suspect it has to do with units here. Well, kind of clear up my thoughts here. It remains, now that we've noted that this corresponds to 1 to 1, it remains to show that any maximal ideal or power x is of this form. So if I just give you random, so suppose I pick a maximal ideal. Now, notice that so let M be just take whatever this maximal ideal is and intersect it down to, well, that would be gamma itself. So let's intersect it down to R. How about that? Right. So basically what we're doing is we're looking at all the constants. Now, what do I know about M? It's an ideal. You can do a little bit better. All right. It's prime. Why is it prime? Well, because M is maximal, so gamma is maximal, so it's prime. And when you intersect a prime ideal down to a small ring, you get a prime ideal. Why is it maximal though?
Since gamma is maximal, if we take the generated by gamma and another element of R, that gives us all R, or actually all the power series, and then we can obtain all R, right?
Right. Let me point out. And is maximal in R, because suppose that you have M as contained in, is another ideal. Then I claim that that n comma x contains gamma, and of course is a proper ideal. And so okay, can somebody explain why n comma x is proper?
I mean, we want a compilation or n comma x is proper?
What's that?
We're looking for a compilation, or you're saying that n comma x is proper?
Well, so let me make this. So here's what I'm gonna do. So I'm gonna make this claim. Okay, first, why is this proper?
Or because n is proper?
Okay. Because if not, then one is in n comma x. So one is in n. We can copy. Right? Why this containment here? Well, this containment here, but suppose that's there. What can you say about f of 0?
Is in m.
If you look at f of 0, I don't know much, but I know that it's not a unit. Because if so, if you start with a unit, this would be a unit inside this prime ideal, which is not possible for power series. Okay, so how does that help?
If zero is in m, then it's in n.
In fact, I claim f of 0 is in must be in fact in n. Right? Not like this here, not ideal. How come? Well, how come it has to be in this end here?
Can you repeat?
Yeah, so what we have here is f of x is some power series in gamma, I'll pick it at random. This represents its constant term. Why does it have to be in n?
Because it's in m.
Well, I mean, are you sure it's in n?
All belongs to R, and m is intersection of
This isn't the intersection, this is what you get under the image of the homomorphism killing the variable. So let me give you an example. So here's consider, let's take it side of it. And So you have the ideal generated by 2 plus x. Let's say that's gamma. And we'll say that f of x is our generating polynomial 2 plus x. Right? What is gamma intersect z? Actually, I probably, instead of intersection, I should, gamma intersect z is 0. Right? But f of 0 is 2. It's in higher ideal. Right, so that's 2 things right here. So I claim that f of 0 must be in this maximal ideal. It must be in a maximal ideal containing m, this intersection down here.
It's in some maximal ideal.
It's in some maximal ideal, and this maximal ideal in particular must contain m. Right? How come? Let's suppose that f of 0 is in a maximal ideal that does not contain. What's the consequence of that? In this case, there exists m and n such that m plus r f 0 is 1 for some r and r. Okay with that? So in other words, when you join f of 0 to this ideal m, if they're not contained in some maximal ideal, then they must be co-maximal. Everybody okay with that?
You're saying that the 0 is in a maximal ideal that doesn't contain m. The 0 can be in the intersection of these 2 maximal ideals, right?
So run that by me again. So
When if we say that S0 is in a maximal ideal that doesn't contain m, even so F0 can be in the intersection of these 2 maximal ideals, right?
okay, so let me do something. I'm worried about losing a little bit. So let me do this here. I'm not going to intersect this anymore. What I'm going to do is I'm going to do the homomorphism. Okay, so let's back this. Let's start here. And this is too convoluted. I can shorten this in place. So let gamma and r power x be maximal. Now, I'm going to cheat a little bit because I already know it's in the form of x. So instead of looking at intersection, let's do this. Let's consider phi from r power x into r given by phi of f of x. So what I'm doing here is just consider the homomorphism from r power x and r given this way, right? Let me point out let m equal the image of gamma. Okay, this will be easier. We can get around it this way, but it is a little convoluted and confusing. My first claim is M is actually proper ideal. Okay. Because if not, then one is in phi of gamma. So there exists a power series of form one plus A1x plus A2x squared in gamma. But this is E. And I'm assuming the gamma is a proper max quantity. Okay. Okay. I now claim that gamma is actually equal to M comma X. Okay. So let's go through it. And gamma. Okay, so let's pick a random f of x and gamma. Notice that A0 is an M by the definition of M, right? So f of x is equal to A0 plus x times A1 plus A2x plus, and this is in M, and this is in X, which is an element of. Right? So that containment is done, and probably not so surprising because M comma X is a maximal ideal, and that gives you right. So an arbitrary element of this looks like M plus A1x plus A2x squared. Right, that's what a typical element looks like. Right. I'm sorry, Rolton.
I thought we had to prove them as maximal.
Well, okay, so that's what we're gonna need, right? So what we wanna do is show that a typical element here is in, a typical element of M comma X is actually in gamma. Okay,
The maximality of gamma, and that's it, right? Since gamma is maximal, any ideal that contain gamma must be equal to.
well, right, but, okay, so take this element here, I'll call it F of X here, MX. How do I know that lives in gamma? Well, if you're right, it is maximality. Consider the ideal F gamma. Okay. I claim that this is a proper ideal. Right? And how do I know that?
M can't be a unit.
Well, so. So first I know that this is a proper ideal, If not, there exists R1X, R, and gamma X. If not, there exists Rx in power series ring and gamma X in gamma, such that Rx f of X plus gamma of X is equal to 1. Right? And what's the problem with that? Well, let's apply phi, so in other words, plug in X equals 0. And I get R0 times M, because f of 0 is M, plus gamma 0 is equal to 1. And what's the problem with that little equation there?
Gamma zero is in that.
Right. This is in M. And this is in M. So 1 is in M, which is the combination.
R0 is an M?
What's that?
R0 is an M?
No, M is.
Oh, the whole element, all right.
Yeah. Yeah, how about that?
Okay, sorry.
So, what does that give me? So, F gamma is strictly contained in R power, so the proper ideal,
But gamma's maximal.
and right, and gamma is maximal. As gamma is maximal, F is in gamma. And there we go. So any arbitrary prime ideal has to be of the form M comma X. Notice that there were a couple places in the proof where this business about the beginning coefficient being 1, making it a unit, was centrally important. And again, like I said, this is not, this theorem is nowhere near true for polynomial rings. So,
That's why it's in that. So
any questions? Yeah.
So after we proved that, that gamma is contained in X, then it suffices to show that MX is a proper ideal, right? And we just cite the max.
Yeah, you're right. I wasn't thinking too well, because this is, you're right, this is I went through more details than I had to, because this is maximal. So if you've got this containment, it has to be, the same as long as it's proper. And of course, this has to be proper,
Yeah.
again, from that unit argument. Okay, so let me give you a corollary to this. So this is, I mean, this is immediate really from the theorem, but it's worth me recording, I think.
Oh, I see.
Corollary, just put this. Whatever, yes. 2 through 10. Here, R is semi-quasi-local. And so is R X.
What's the definition?
It's finitely many.
Right,
But not necessarily.
right, and so what I mean by putting in the semi input, so this means if R has only one maximal ideal, then this is also true of Rx. This means if R has only finitely many maximal ideals, so is R of X. And actually, I will, just to get on your nerves, go a little bit further,
But not these quasi as well.
is, and this is, so this will be a corollary to what I'm gonna write now. that I don't think I've recorded yet on theorem. You know. Theorem. Then. So.
What's corollary? Go both ways.
Well.
We have that bijection.
If you have a ring, so the corollary, so this is sort of a corollary also to the next thing. If R is Noetherian, so is R power X, right? Ring of identity. And so, and also, if you have a ring of identity, if R power X is Noetherian, and so is R. And so, remember, this quasi business is the possibility of not being Noetherian, right? So this actually means semi-quasi-local plus Noetherian, and local means quasi-local plus Noetherian. Yeah, I really apologize for that awful terminology.
Right, I'm just saying like, the if then can be changed to an if and only if.
Where, right here?
Yeah,
Yes.
okay.
By the way, I'm gonna sketch the proof of this, just like I did with the Hilbert basis theorem. I think at some point we need choice here, maybe, but we'll see. How would you go about this, you think? Actually, the reason I want to sketch this proof is because this result is true for power series as it was for polynomials, but the proof, I think, is very different. If you remember what we did with polynomials, we looked at what the leading coefficients, we looked at the ideals generated by all the leading coefficients that was finitely generated. So we picked out some polynomials that generated the leading coefficients. And then at the largest degree, so everything beyond the largest degree of those polynomials that generate the leading coefficient, we're good to go behind there. And then we start throwing in stuff below. You can't do that here, right? You can't do that. So here's what I'm gonna do here. Strategy. Show every prime ideal is finite generated. And I'm not gonna do a complete proof, but I'll give you the idea of how to do it. So let's suppose and here you will see, I think very quickly, why prime is important here. Suppose gamma in R power X prime. And again, you can see the homomorphism phi from R power X into R given by phi of f of X is f of 0. So so this is the homomorphism that basically just cuts the head off the power series, right? And you look only at the constant term. Okay. There are two cases to consider. Case one. Suppose that X is in gamma, right? This is the easy case, actually. In this case, if, in this case, I claim that gamma is phi gamma, comma x. So, let me justify this for you. So in other words, what I'm saying is if X lives in this prime ideal, then basically it's generated by the constant terms in X, right? So here's the first bit. So notice that if I pick anything out of here at random, then the constant term is in here. And of course, the tail of it is in it. So f of x, which is f of 0 plus a1x plus a2x squared plus is equal to f of 0 plus x a1 plus a2x plus, which is in phi of gamma comma x. And the other containment depends on the fact that x is in gamma. So what's that now?
Since X is in gamma, we only need to prove that P gamma is in gamma. But if you take a generic element of P in gamma, it's because there's an element in gamma such that the constant term is equal to that element, and you can subtract the X times
That's-
something.
That's it.
That's it.
So, um, now you need to prove this is in gamma, right? And as you pointed out, since x is in gamma, it suffices to show that f of 0 is in gamma. Right? But notice, of course, f of 0 is just the image of some power series in gamma. Since f of x is in gamma and x is in gamma, then f of 0, which is f of x minus well, actually, I guess I can technically write that out. Let me write it this way, just so we can see what's going on. Then f of 0, which is f of x minus x times a1 plus a2x plus is in gamma. So let me point out also that in this case, we're done with the proof here, but let me make a useful remark. Prime. Right, because the prime ideal gamma is of this form, and that forces phi of gamma to be prime, right? Notice that this is, I'll bring this up. Following reason, and that is actually, getting the car ahead. in this case, theta gamma is prime. I didn't finish my thought here. So gamma is theta gamma x. So let me finish my thought here. And this is finite generator. As the of gamma in R is an ideal and R is Noetherian. So, okay. Let me give you a quick example before we do the next case. If you look in Z power x, the ideal generated by the polynomial 4 plus x actually is prime. We saw last time that this was an irreducible. Y'all remember that? And it turns out that Z power x is a UFD, so if it's an irreducible prime. Be careful though, because in this case, phi of gamma is the ideal generated by 4. And this is not prime. So you have to be a little bit careful. In the case though, but of course, this prime ideal does not contain x, right? Okay, so what's the second case? The second case is this. Suppose now that x is not in. Okay, so what happens in this case? Well, I claim well, anybody know what how to prove that it's finally generated here? Maybe, so consider this. In this case, consider let me say a couple of things about this. It's an ideal and it's proper. Notice this would not lend itself very good to polynomials. The reason it's proper is because what you're looking at is the constant terms. None of them can be units, right? This is not true for polynomials, right? You might have the ideal generated by 1 plus x, which is a non-unit, and the polynomial. Since R is Noetherian, gamma 0 is generated by, let's say, A0, A1, A2. Index human being, A1, A2, AN. I don't know much, but I know that ideal is fine. Find at random F1, F2, Fn, and gamma such that Fj 0 is AJ. So just find any power series you want whose leading term is, or constant term is A1, another one whose constant term is A2, and so forth. And I claim in this case, so for me to really do this inductively, I'd have to do it inductively. I'm a lazy person. This is sort of like my high school division argument for units in a certain sense. So forgive me on this. We have to make a lot of choices. In this case, gamma is generated by F1, F2, Fn. And let me show you intuitively how this process works. Suppose you have gamma, x in gamma. So let's write gamma x. Gamma 0 plus gamma 1x plus gamma 2 squared plus. Now, gamma 0 is in 0. So this is a linear combination of A0, A1, right? So there exists R0, let's say, right, there's this R1, R2, Rn, such that gamma 0 is R1A1 plus R2A2 plus Rn. Correct? Right. Now, consider gamma of x minus now, what can you say? So notice that these are exactly the RIs that I use up here. What can you say about the so notice that this power series that I put together is actually in gamma, right? Because all the FIs are in gamma, so this is still in gamma. And what can you say about
The constant term is 0.
the constant term is 0, right? So I know that this can be written in the form xk bk plus xk plus 1 bk plus 1 plus n gamma.
The X is.
But x is not in gamma. But as x is not in gamma, then it's the case, since gamma is prime and x is not in gamma, then bk plus bk plus 1 x plus etc. is in gamma. Which means that bk is in gamma 0 again. So now you can write this as a linear combination of the AIs and subtract something further off of this. Right? And what happens is, so now you subtract R1 times the power of X F1, R2 power of X F2, and so forth. And basically what happens is at every iteration, you get a higher and higher power of X. This goes to 0 and the exact goes to 0, the intersection of X and the end is 0. And basically, inductively, you can do this more carefully. You can come to the conclusion, after making a lot of choices, is R1X, F1 of X, plus RK of X, FK of X. Only, not K, I mean M. Right, so subtract off this first wave that kills the first term, and what do you get? You get a power series that begins with some larger power of X. Well, you also know that this thing, the constant term here, if you will, after you divide out by X to K, the constant term here is also a linear combination of this. So now you can augment this and push this down further and so forth and so on. And so you get the F1 up to Fn, or your finite generated set, right? That's not a careful proof, but I suppose it gets the idea. Is there any questions about that? You're dying to ask a question, Eric. I know you are.
I don't understand it well enough to ask the correct question.
Well, so sort of think of it as a partial sum sort of thing, right? So you start off with gamma x, and our goal, if you will, is to write it as a linear combination of these power series that begin with the things that generate the leading coefficient. Well, gamma x minus this is now this polynomial that's missing at least the linear, at least the constant term, if not others, right? Well, if you divide out by xk, this is again a linear combination of leading terms, right? So now you can subtract off some other x to the k times, some other r times f1 and so forth. You do this infinitely often, if you will. And at the end game, what happens is this vanishes because the intersection of all powers of x that you go to infinity goes to 0, and what you're left here is gamma x minus power series. So take it over the other side, and that's where these power series here come from. Right? So think of it step by step. You're driving the powers of x up, right? And every time you see a new coefficient that comes out of the leading coefficients, you can now use the power series F1 up to Fn again to eliminate that, dropping it down further and further. That's the gist of it. And, be grateful that I didn't put this on the homework, to do the, careful induction, because it's obnoxious. Okay. So I'm going to start, and not get very far, on the next topic here. So we talked about polynomials, we talked about power series, you talked about local rings, localizations, quasi-local, this kind of thing. And we did mention valuation domains, which I did a few examples. Now, these ideas are going to come back, actually, especially that evaluation domains, when I talk about integrality. So, okay, so how many of you have had 85-20? Right? And so you spend, how many of you have had Galois theory and things like this? Fields, extensions, Galois theory? Well, so this is sort of what commutative algebraists do. That's the generalization of kind of the notion of algebraic here. So what does it mean to be integral? In this section, R will usually be a domain. When it is a domain, I'll say that T is an overring and K is its quotient field. Definitely. Let R be a commutative ring in T and R algebra. And I'll explain this. Let R be a commutative ring and T and R algebra. And I'll go with what that means later. An element T is said to be integral over R. To the integral over R. If T is a root of a monic polynomial, and I'll write this out for dramatic purposes. Xn plus Rn minus 1, Xn minus 1 is R1x plus R0. So we say an element in So think of T right for now as just be a bigger ring containing R, is integral if it is the root of some monic polynomial in Rx. Monic just means that the coefficient of that leading term is one. If every element, every T and T is integral over R, we say capital T is integral over R. Or in the case of a ring containing R, we can call it an integral extension. Okay, that's enough for now. Any questions on that? I'll talk about what an algorithm and give you some examples and talk about this before we kind of get into the meat of it next time. I encourage you to be at Math Club if you have the time to. Otherwise, y'all have a good weekend.